including the Poincare conjecture and the quarter pinching sphere theorem, which has been open for 60 years. There was absolutely no other ways to solve it except by using the rigid flow. So many important questions have been solved by rigid flow besides these two important conjectures. And Richard Hamilton is a key person into it. And rigid flow does not die because it works in Kähler geometry and it works in four manifold. We were hoping that rigid flow could be important for the four-dimensional Poincare conjecture, or at least the development of four-dimensional manifolds. This will take more efforts, and I assume that younger mathematicians in this audience probably will take up the torch. But anyway, it was a misled report by many reporters, either in news media or some magazines, that Hamilton started rigid flow and did not do much until Perelman. It's absolute nonsense. I remember I met Richard Hamilton in 1978 in Cornell. Rick Shen and I was working on harmonic maps, and we were interested to know whether Yu's and Sampson's work can be reformulated in the space of metrics. Well, little do I know, when I met Hamilton, he actually has already started and even proving the local existence on the rigid flow. So I thought that's great, but I thought I would wait until to see something serious coming up, namely global existence. And I thought that would be very difficult, arrogant. And then by 1982, I got a phone call from Richard, who told me he could do the three-manifold case with positive rigid curvature. That really shocked me and totally amazed by his argument. He'd come to Institute for Advanced Study and study the rigid flow and give a big report. It was spectacular. I immediately get 3 of my graduate students to work on the subject, Kähler rigid flow and curvature flow and all that, and start to look into what Hamilton done. And this is really spectacular, but then there's a long journey to go because we need to know how to pinching, how to not get rid of singularity, how to handle singularity and all that. So at that time, I knew there would be at least 20 years work in order to make it work. But it and plan on it, and he started to do amazing work. There are a lot of obstacles he has to overcome. He overcome one by one. And some of this he will report today. By 1996, actually, when he proved that geometrization problem can be solved if the curvature is bounded, I see the rest should be doable, and so many people started work on it. This problem. Unfortunately, NSF did mathematical biology, which did not produce much. If NSF would fund this center in Hawaii, I'm sure we could have done much more than what we have done. Well, in the last step, I mean. Leader, Perelman come in and provide really, but even in the last step, there are quite a lot of people has made a contribution to it to accomplish the final step. Stop there because the rigid flow is still continue to play a very important role. So Richard is going to tell you some more details. So Richard.
Tang Yao is a good and he was one of the first people, actually the first, aside from the importance of the Ricci flow. And he has done a great deal to me and my work on the subject, and encouraged many Dong who's done excellent work. So I think I'll start by telling you the story. How did I think of the race? Two ways the story goes. How someone should have thought of it, and how they actually thought of it. So how I should have thought of it is that minus twice the Ricci curvature is actually a natural substitute for the Laplacian of the metric, which does. And so it's natural to write down the heat equation for a Riemannian metric as d to be minus twice Ricci. That's not how I found it. I was motivated by the work of Ilse and Sampson on harmonic map flow. And when I had to scramble around and learn differential geometry, which I learned out of a lovely old book by Eisenhower. I don't need it yet. Let's see, where was I? Yeah, I was motivated, and I thought it would do a heat type equation for a Riemannian metric. So I thought, well, else would be length of the first derivative of the metric squared and doing the gradient flow. Unfortunately, yes, you all know, in the natural sense, the first derivative of the metric is the component. So that doesn't exactly, which I learned from my son Andrew, who at the time had come up to visit me. He was a teenager in Ithaca, New York. I was car, and I had parked it overnight outside of it. I could move into my apartment, and I was with Andrew, and I started driving, and after about 2 feet, there was this loud clunk, and I got out and looked at one of the wheels had fallen off the car. So I went back in the car, put my head in my hands, and my son Andrew said, "What's wrong, Daddy?" And I said, "The wheel just fell off the car." And he said, "Hey, Dad, I couldn't find the steer energy to do the gradient flow, but I thought, well, what would I do next?" I thought, well, the gradient flow would involve first to do the gradient flow, you'd get something in second derivatives of metric. And then the alarm bells went off. The T of the metric is plus the Ricci curvature. And then I calculated ddt of the Riemannian curvature. Clearly the wrong way. That so that's how I came up with the Ricci curvature. So it really is a heat equation for a metric, and what the regular heat equation for heat tries to over the fold. Now I think at this point I can start doing my slides. So I don't bound by V1 and Vk, where k goes from 2 to the dimension n, and the manifold is, and the initial Ricci curvature is positive, that actually happens. I'm going to do something with it. And he said, confessed to me later, "Oh, when you first showed me the Ricci flow, I thought you were a madman." I love the idea that, and so then, so as I say, that the first theorem was there, easy to get, but in 3 dimensions, the converge to constant positive curvature. Proves the theorem that if you have a 3-manifold with positive motion of the sphere by a group of linear isometries. However, Yao pointed out to me that if you don't have that as three, so that they're not too trivial, and you have a neck connecting them, and the neck looks like a cylinder, an S2 than the others, and that like closes down the neck and pops a hole. So that my father was a doctor, would go to lunch downtown, and walking down the street, I could never go more than a block, but what two people came up to thank my dad for saving their lives, and then they'd tell me how great my dad was. Very nice. So anyway, in the intestines, I would think of the part of the neck with the high curvature. Manifold goes into the hospital, and cut out the part there, the curvature, sew it up. That's how I came to everything. To make you more Ricci flow, I thought it would be best just to give you flow would be on an Einstein manifold, where the Ricci curvature is a multiple of the metric. And of course, if the multiple is zero, she's zero, and then the Ricci flow doesn't do anything. Hard to describe. Nothing is hard to describe. So anyway, the behavior of the Ricci flow depends on the sign of the constant. When this constant G is positive, the metric shrinks. So on a round sphere with equal if C is negative, then you get the opposite thing. It will expand, which is what I think many physicists have said is supposed to happen to our universe. I myself. So those are the examples. So now to some more interesting examples. There's where you get these things that move without changing their shape, and the thing like they look. Well, anyway, if it moves, change in the class the cigar. Basically, you add a constant at any other time, and what it looks like is this water cylinder, written 3 wavy at the end of it, indicate that it. But then it looked like the smoke, the cigar. Just how I got opening like a paraboloid, and its existence was first proved by Robert Bryant. Then there's another one found by Eli at Berkeley. It's kind of hard to draw in 3 dimensions. Each curve here you should think of as rotating around to all look like a bunch of solid up and to both ends at an angle. I called it the fly because they signed in a plane and an angle wing, that would fly and take. Okay, so now there's some examples in 3 dimensions that are homogeneous. An example is 3 number of homogeneous metrics. So I'll remind homogeneous where there's an isomorphism any point to any other point. So it looks the same at every point, not in different directions. Use this using these fields A, B, and C in X, Y, U, V space, and they're arranged so that the Lie brackets come out nice. B is 2C to B, and C is 2A, and A is 2B. And then if you look at the homogeneous metric with the diagonal elements like this, and if they have values alpha, beta, then the Ricci flow turns into ordinary differential equations. You'll see there are various combinations of alpha, beta, and gamma. And they could solve numerically. Computer
whether one can use not just length, but maybe heat equation, curvature flow, or some other things to solve problems in group theory or in algebra?
Oh, that's a great question. And I don't know the answer. I don't know much about group theory or algebra. I do know that there's a whole wide field of geometric flows now. And the curve shortening flow is basically a heat equation for a curve. It flows every point on the curve with a velocity equal to the curvature in the normal direction. And it's an unusual, surprising theorem that if you start with an embedded curve, it will actually stay embedded up to the point that it straightens out to a little circle and shrinks to a point. And that was like greeted with skepticism at the beginning, because people drew examples of curves that would wind all around with a spiral and spiraling in and out, and thinking, well, how can it unwrap itself without doing a singularity? But it turns out it does. And so that's a beautiful example of a geometric flow. There's an interesting conjecture by a student of mine, Steve Altshuler, who worked on the curve shrinking flow in space. And for the curve shrinking flow in space, even with an embedded curve, you can form a singularity. And the way that happens is you can have a curve that comes down, makes a loop, and goes on, and the loop almost crosses itself, but it goes to one side or the other. And then if you play around with a one parameter family, you see that there has to be some curve there which is going to do something singular, and that one curve, instead of going straightening out to one side or the other, actually makes a cusp. So Steve Altshuler's conjecture is that generically, like for an open dense set of initial curves in space, you don't get any singularities. It would be a nice example of proving something that happens generically. I don't think we have many results in the field of geometric flows on generic behavior. Okay.
Are there other questions to ask Richard? Yeah.
Thank you for your wonderful talk. I just want to ask that if it's possible to take the time as another coordinator and consider a manifold with one dimension high, and whether there are some good geometric structure on this high, on this possible high dimensional manifold. Thanks.
I guess I didn't quite understand.
So I just asked.
Well, maybe Yao can explain.
Sorry.
Relativity, where space and time put together.
Oh,
like general relativity.
Thanks.
Well, the thing with general relativity is that it has a Heisenberg metric. One of the dimensions, the time usually is counts as ds squared is dx squared plus dy squared plus dz squared minus dt squared. And that leads to hyperbolic type equations. They're not exactly hyperbolic, but they're similar, and they can produce singularities. But if you tried to run Ricci flow on a Heisenberg metric, you'd encounter a problem that in the time-like directions, you would be running a backwards parabolic flow. And you can't solve a parabolic equation backwards. If you try to solve df dt as minus Laplace f, well, what happens is with DDT equals plus Laplace F, the high frequencies decay away fastest. But with the negative equation, df dt is minus Laplace F, then the highest frequencies blow up fastest and you just get garbage. So I don't know how to reasonably answer that.
Okay, other questions?
Okay, thank you. Also, thank you, Professor
No,
Yeo.
sit down, please. Other questions?
Mm.
Yeah. Witten.
I think the last question was not intended to be about Ricci flow in Lorentz signature. Rather, the questioner was asking the following. If you have an n-dimensional Riemannian manifold, and you take a one-parameter family of metrics due to the Ricci flow, do you get something that you can usefully regard as a geometrical structure in n+1 dimensions?
Oh.
I think that was the intended question.
Yeah. You could certainly regard it as that, but I don't know that it would. I mean, you're not actually getting a normal Riemannian metric in space-time. So I guess I don't know how you would
I don't think
profit
it
from it.
is too much useful to look at it that way. Okay, other questions? Well, if not, Richard, you want to continue or you want to make remarks?
I've run out of the material that I prepared because of some problems with the computer, but I'll make some other remarks. One thing is that there has been recent progress on the curvature pinching. And the original work by Klingenberg was on quarter pinching, making it homogeneous to a sphere if it's simply connected. So there's a lovely work by Rick Shane and Simone Brendla on doing versions that are conditions that are stronger than quarter pinching, in like imply quarter pinching, but under Ricci flow evolve to nice round things, and that's worth mentioning. Yeah, and also there's various other estimates that are useful for Ricci flow that are rather technical, but one is the Harnack estimate, and the Harnack estimate is you have to prove it as a matrix inequality, but the ordinary Harnack estimate for the heat equation basically is that df dt plus 2 df dot v plus f length v squared is going to be plus 1 over tf is greater than equal to 0. And that has nice implications. And we have a Harnack estimate for the Ricci flow. And we also have a logarithmic Sobolev inequality, which is due to Perelman. Perelman is a very clever fellow. And he has a slight version on the logarithmic Sobolev quantity in which he includes the scalar curvature. And then its evolution under the Ricci flow is you just do ddt of this logarithmic Sobolev quantity. I won't want to call it a constant because we always talk about the Sobolev constant, but you can't talk about the constant evolving so easily. So anyway, it's a very nice result, which implies that if you have a pinching condition initially, volume pinching, so you assume the volume of a ball of radius r for small r is at least some constant kappa times r to the n, that you then get, if that estimate is true for an initial time, you can say that you get a similar estimate for a later time, but the constant kappa has to change, and it's going to decrease exponentially. So that means that when you do limits of Ricci flow, they can be collapsing. And one way to deal with that is you have to expand not just to control the curvature, but also to control the volumes. So there's a bunch of stuff that can be done that way. We have these nice, powerful estimates. Okay. I also had a version of universal pinching estimate. That the pinching is that if you run Ricci flow, say in some dimension, like in 3, it can have some negative curvature, but the negative curvatures tend to come up, and they kind of get all pushed towards non-negative. So, yeah, that's an interesting idea. Lots of other interesting ideas, lots of problems to work on. In 4 dimensions, I and others have worked on hypothesis of positive isotropic curvature in 4 dimensions, and that produces useful results. Any other questions?
Yeah, so perhaps we could ask more questions. Some questions for fun. Yeah.
Can we apply the Ricci flow to prove the Stokes conjecture on positive Ricci curvature?
To the what conjecture?
Stokes conjecture on positive Ricci curvature.
Stars?
Can you explain exactly what you said? I don't quite catch what you said. What conjecture?
Stokes.
What?
Stokes conjecture on positive Ricci curvature and the stream Poisson.
You mean the sole conjecture that was done by Perelman many years ago?
No. The positive Ricci curvature and the stream Poisson. The relation between stream Poisson and the positive Ricci curvature.
I don't quite understand exactly what you state the conjecture, the statement.
No, Stokes.
Can you state exactly what the conjecture is? You mentioned the Stokes, okay? Make a statement.
The manifold admits positive Ricci curvature if and only if the Witten genus vanishes.
What dimension? All dimension or dimension 4?
No, any dimension larger than or equal to 5.
So you say that he conjectured that manifold has positive Ricci curvature, even only if the Witten genus is equal to 0. I thought that makes an assumption on the Pontryagin class. Assume the first Pontryagin class equals 0.
Yes, yes. It requires the string structure.
Yeah.
1/2 P1 equals 0.
Yeah. Well, Richard, so there was a conjecture which I don't believe is true, is that if I assume the manifold have first Pontryagin class equals 0, then
First what class?
First, number 1, Pontryagin class.
Quadratic.
The
Pontryagin class,
Yeah.
okay.
Then the manifold admits positive Ricci curvature if and only if some topological invariant Witten genus equals 0.
Well, if you were trying to prove that with Ricci flow, you kind of need a metric to start with.
Right.
And it's not clear where you would start. And if you just start at random, you're likely to get neck pinch singularities.
So maybe I add to the comment, because the work, the WISE three-dimensional work is because Ricci positivity is preserved. Once you go on dimension 4 or more, it's no longer the case that Ricci will be preserved. So even you assume at time t equals to 0, you get positive Ricci curvature, it will probably does not, for once you evolve. So it's not clear, right, Richard?
Yes, thank
So
you.
probably have to be by other means.
Okay, other questions? Any questions for fun? Yeah.
Richard, can you comment on other curvature flow that might have applications in other areas?
Oh, well, I can tell you the various curvature flows I've thought of. Certainly the most important is the mean curvature flow. And the difference is with Ricci flow, you just have an abstract manifold. It doesn't have to be in a Euclidean space. And if it did, the Euclidean space would have nothing to do with it. The mean curvature flow, well, Ricci curvature is an intrinsic curvature. Mean curvature is an extrinsic curvature, meaning it describes how the manifold curves in an enveloping Euclidean space. And I like to think of the Ricci flow and the mean curvature flow as twins, but not identical twins. In that I think they kind of seem to share half of the DNA. That half of the things that work for Ricci flow also work in mean curvature flow, and half are just totally different. I know my good friend Gerhard Huisken has done a lot of good stuff on mean curvature flow, as well as many others. I was lucky that back shortly after I'd first moved to San Diego, and while Yao and Rick were still there, Gerhard Huisken came to visit in San Diego, and I got to work with him for a whole year. And we discussed a number of ideas, like limits of manifolds, for which I have to thank Rick Shane for a very good tutorial, and compared the different things between the mean curvature flow and the Ricci flow. So, and as far as applications, I don't really know. There was one application which used the inverse mean curvature flow, where you flow the manifold by -1 over the mean curvature. That was used to prove, I think, the Penrose conjecture. And that was nice. It involves singularities. Yeah.
Well, actually, the mean curvature flow is related to Ricci flow for bundles in a more precise manner. Under Miller symmetry, the mean curvature flow, the special Lagrangian cycle, is actually Miller to the Ricci flow for bundles, for Hermitian-Young-Mills metric. So that was more or less can be proven in some way to be the case, although it's still a conjecture. It's a conjecture that Richard Thomas and I made 30 years ago. So far is fine. The only thing I can say. Any questions? Yeah.
Hi, thank you for the wonderful talk. Real quick, because I can't help myself, is your cell phone called McNugget?
Well, I hadn't thought of that, but maybe it's a good idea. boundary and doing the similar result with a boundary. For example, my book on harmonic maps of manifolds with boundary. What I've tried with the Ricci flow, I think it makes sense to have the Dirichlet condition of try to specify the metric on the boundary. I'm trying to remember. I think there's something like it's a different number. I think maybe you have to specify one less boundary condition. God, that was a long time ago. But I never really found one that seemed particularly useful. I think that Dirichlet boundary conditions make sense, but the Neumann boundary condition only made sense if you could double the manifold to account for that. Yeah.
Thank you.
Okay. Other questions? Yeah.
I'm asking a question about applying Ricci flow to four manifold. So if you have a Ricci flow or some kind of generalized Ricci flow, for four manifold, have long time existence, it may lead to a complex manifold or symplectic manifold, and with divisors or cycles cut out. Can you make some comment on this four manifold?
Well, I've worked on a bit on Ricci flow on four manifolds with positive isotropic curvature, which is an unusual curvature condition, but it seems to, it's preserved under Ricci flow, and it will lead to good convergent results. Aside from that, I don't know. But it's certainly an interesting thing to study. And
yeah.
Okay,
yeah.
next. Yeah. The back. Power now. Some people in the back.
Hi, can you say something about the four-dimensional Poincare conjecture, whether Ricci flow will, the advantage of Ricci flow to solve it or the obstructions?
4D Poincare conjecture, was it?
Yes, yes.
Gee, that would be nice. I think that it would be hard. I think that there's a lot of structure that can go on in four manifolds, and one would have to figure out how to deal with singularities. But I think it's potentially very useful because in 4 dimensions, let's see, you get two possible singularities. You get the classic next pinch, where an S3 cross R1 pinches down, and let's see, and then there's a hole punch singularity, which you can envision in the following way. You take a sheet of two spheres over the two plane, and imagine that the smallest sphere is at the origin, and the spheres grow in size as you go out away from the origin. Then the small sphere will shrink fastest, and it will close down to a point, and then the ones around it will close down, and you'll get this disk where the spheres have all collapsed, and it's opening up a hole in the manifold. So that's certainly a very interesting singularity, and it's going to be a lot harder to study than the neck pinch. Like, for one thing, if you try to do surgery on it, where would you cut? That you could get very irregular shapes to where the hole has formed. I've discussed that with Huisken, but I don't know that anybody's been able to do anything with it yet. If somebody in here has, please come see me.
Carl want to say a comment.
Maybe I add a couple of comments. First of all, as Richard said, the singularity will be besides S3 cross the interval, that's neck pinch, you will have S2 cross two-dimensional, like R2 or square. So that's what he called a hole punch, and that is very tough singularity, how to do surgery. Second, I want to say is even in 3 dimension, the simply connectedness assumption was not used in the, say, Poincare conjecture in the process. So how that simply connectedness was used is at the very end. So you do the Ricci flow and analyze singularity and do the surgery. And then if it's the compact case, you have the finite, you got the finite extinction time proved by Paraman and also different proved by Cody-Minikowski. And then you know basically how the 3 manifold look like. It's the connect sum of special pieces. And then you look at those lists and apply the simple connectedness and say, aha, that must be S3. And that's how is simply connected was used. So maybe one should, even for 3-dimensional, or in the case 4-dimension, is explore whether one could more effectively use the simply connectedness assumption. And that is will be a great, yeah.
Real quick, one more remark, that if you did Ricci flow on a 5-dimensional manifold, then there's a surgery that you can do, which is, I guess, B3 cross S2 going into B2 cross S3. So the surgery can do itself both forward and backwards. And in that case, you probably are not going to be able to control the topology up to diffeomorphism.
I think the Poincare conjecture 4-dimensional manifold is probably better changed to replacing the S4 by CP2, complex projective 2-dimensional space, because that one involves complex geometry, and complex geometry, we know CP2 is rigid. Once you know it's diffeomorphic CP2, then it's actually the standard metric, more or less. And once you use the anti-Scherf-Due part of the curvature much more extensively, which so far has not been used. And there is a paper by Cliff Taus, written about 30 years ago. He proved that after stabilized 4 manifold, there exists an anti-Scherf-Due metric. This paper has not been recognized by most people, which should be recognized, I think, because anti-Scherf-Due condension is very important, and so far has not been used.
May I add, Professor? So actually, Professor Hamilton has proposed a problem precisely using Tauf's work that Professor Yao mentioned. So this will be something called half PIC. Maybe I explain in my lecture tomorrow.
Sure.
Yeah.
Okay. Other questions? Yeah.
Thank you very much for your wonderful talk. So can you comment on the existence of non-Einstein compact Ricci soliton? Thank you.
Non-compact Einstein Ricci soliton.
A non-Einstein compact Ricci soliton, because it seems rare than the compact Einstein.
Ricci soliton that are not Einstein metric.
That starts in dimension 4. And actually, on dimension 4, we have 2 examples, but they are both scalar. So one is on CP2 block 1 point, which Koizo and I found in late 80s and early 90s. And the second one is CP2 block 2 points. And that was by Xu Jiawan and Xiaohua Zhu about 20 years ago. So those are actually, so far, the compact example, we only have those two, and there'll be two non-compact. And they are all scalar. So far, we only know scalar examples. So there's a classification dimension 4. The shrinking examples are precisely two compact and two non-compact ones. And it's an interesting question whether there will be any non-scalar ones in dimension 4, and that remains to be seen.
Okay, next question. Yeah.
One application of Ricci flow in physics is that it's the renormalization group flow of the 2D nonlinear sigma model, and but it's only the one loop renormalization group flow, and this so there are some higher loop corrections. I wonder maybe this can suggest some variant of Ricci flow, and whether this will be useful also in mathematics.
Oh, yeah. I was trying to learn a little bit about that. There was, I think, a paper of Dan Friedan who pointed out that Ricci flow was what the one loop approximation to the renormalization group. And maybe a two-loop approximation would be interested, but I think that led to a fourth-order PDE. And it's much harder to analyze fourth-order PDEs. It would be a very good field of study, but the problem is you don't get the maximum principle. So our main tool is missing.
Okay, I think time is up, and we thank Richard for a beautiful talk. We come back at 9:45. Thank you.
And there are actually some work on that set, loop approximation. Brilliant.
So have a seat, please. We need to start the next lecture. Could you lecture give me man? Title. Please come in and sit down. Okay, let's start the next lecture. So Alexei Kitaev is awardee of the physics part of the conference. I've known him for about 6 or 7 years. When he visited Harvard CMSA, he was working with Dan Free and Mike Hopkins in those days. And they have some kind of meetings constantly each year to choose Harvard in my institute, CMSA. And he was more quiet than what I thought. I'd like to talk with you more. And I was in the physics department. There was discussion on how to recruit him to come for even just short visit. It was not easy. So I was very pleased when we announced the award to him. He accepted instantly, which I'm really very grateful that he will take this offer to come. And it was really an important event that he will come. And he is expert on quantum computing, one of the founder of quantum computing and statistical physics. Schubert has talked about his work on Sunday, so I would not repeat it. But we will listen to his work, which is extremely important today, called Chaos and Black Hole. So, Alexei, thank you.
Thank you for the kind introduction and for the invitation. It's a pleasure to me to speak here in this audience. My talk will be about chaos and black holes. And as you can tell from this picture, it's a kind of toy version of a black hole. So it's a highly theoretical talk discussing connections between different mathematical models. But those models can shed a light on interesting physical phenomena. This is the outline. Chaos is something unpredictable and irregular, but this is not a good definition. We may not be able to predict things because we don't understand them. And a better definition is that chaos is related to fundamental unpredictability. it's like it is impossible to make weather forecast more than for a few days, because a small change in the weather conditions now will be amplified later, and in a month, even a flap of butterfly wings will affect the weather. This is classical chaos, and it's pretty simple. I'll say more about it in a minute, but the main subject is quantum chaos. Quantum chaos is less intuitive. It's described by out-of-time order correlators. We consider the product of operators applied at different times, and those times should alternate. And this way we construct a quantity that is analogous to classical observables and that is sensitive to chaos. There are many chaotic systems, classical and quantum. I'll focus on two systems or classes of systems. One is black holes. This is an image of an actual black hole in another galaxy, in the center of a galaxy that can be seen from Earth using radio telescopes. However, the subject of my talk is related to subtle properties of black holes that are not easily related to observations. Space-time geometry can be related to observations, but there are parts of the black hole that are hidden from sight. Oh, what happened? Oh, it's back. Yeah, thank you. I hope you saw the previous picture. There are part of black holes that are hidden from sight, and in this picture, there is a physical region and some regions inside the black hole, and the boundary between those regions, which is called horizon. Those are not seen directly, but we can study them theoretically. The next picture illustrates Hawking radiation. It's a quantum effect in black holes. As Edward Witten said in his lecture yesterday, Einstein gravity and quantum mechanics do not combine well, and to combine them, one needs a more advanced theory like string theory. However, some simple quantum effects can be studied within the framework of Einstein gravity. They do combine if we don't go to very short distances. And Hawking radiation is one such effect. The other effect is called Drake-Hooft effect. It's both classical and quantum. Classically, if we throw an object into a black hole, it's gone. We never see it again. However, this object creates a perturbation of space-time inside the black hole. And this perturbation can be regarded as a shock wave concentrated in the vicinity of the past horizon. Hawking radiation particles pass through this shock wave, and the state of the radiation is affected by the shock wave. But it's kind of like a butterfly. We cannot detect the presence of a butterfly just looking at the weather around. We don't know whether it rains because of the butterfly or for some other reason. And the same is true of Drake-Hooft effect. I'll explain it later in more detail. The other class of systems that exhibit chaos is large N models, including the Sajiv-Yakitaev model. A large N system is a system of simple degrees of freedom, like spins of fermions interacting with each other. And they interact all to all. Every pair or every group of 4 particles are coupled to each other and interact. This is an illustration. The Sajiv-Yakitaev model is special in that out-of-time order correlators or chaos in that model are similar to chaos in black holes. And this is because the SYK model has a soft mode, a collective mode. We know collective modes in condensed matter systems like sound is a collective mode in a system that is built of atoms. But in this case, the collective mode is more interesting. It's a reparameterization of time. You can think of time as a spring, and I've drawn a circular time, which is imaginary time, so-called Matsubara time. And there is a collective mode that involves deformation of the time spring, and it's also related to geometry. So let me start from the beginning. The butterfly effect. A flap of butterflies' wings can change the weather. We believe this is true because the Earth, with its atmosphere and ocean, is a complex, chaotic system. But it's too complex. Let's consider a simple chaotic system, the stadium billiard. This is a billiard, and this is the trajectory of a ball that bounces off the walls and moves without friction. And you see that the trajectory is kind of irregular. How do we understand that? To understand it, we need to first write down the equation of motion, and those equations can be written in terms of 4 variables. There are 2 coordinates, Q1 and Q2, and the corresponding momenta, P1 and P2. And that whole set of 4 variables is the full description of the system state. The state evolves in time according to some equations. And if we consider 2 trajectories with slightly different boundary conditions, the difference is amplified over time such that the trajectories diverge. You see the red trajectory and the green trajectory diverge, and they diverge exponentially in time. And the exponent kappa is called the Lyapunov exponent. The exponential divergence of trajectories is the hallmark of classical chaos. This is a simple mathematical phenomenon. It can be seen in simulations, but is there a direct way to measure chaos? The problem is the absence of reference data. So I'll pause for a moment and let you think about a way of testing this theory. Okay. There are 2 tests. Test 1, run the Earth's time or the Earth's dynamics forward and backward, and we can describe a particular experiment. Begin the experiment at time 0, advance the Earth's time to t, and record weather data. Then we run the time backward, introduce a butterfly, and run the time forward again. And finally, we compare the weather now with the recorded weather without the butterfly. And test 2 is to do the 2 runs in parallel using 2 copies of the Earth. Of course, it sounds ridiculous. That's in part because the Earth is such a big system that we cannot control it. Let's talk about control. This kind of tests can actually be done on small systems, but they require very precise control. If we are to do such a test on a classical system, the required accuracy should be exponential, such that errors in our experiment are smaller than the amplified errors due to the divergence of trajectories. This requirement can be met in a simulation because we can increase the number of precision digits, and we can use the number of digits proportional to the simulation time. In an actual experiment, it's very hard to do. So it can only be done for very short times. But for longer times, the exponential dependence stops and quantum effects become important. For quantum systems, the scaling is more favorable. The required accuracy is n times t inverted. And this number says that there shouldn't be any error at all during the simulation. an error would be, say, one photon or one phonon absorbed during the simulation. It's a stringent requirement, but it can be met using high-quality qubits or a small system like several nuclear spins in a molecule. Now I would like to discuss quantum chaos. And I need to begin with some introduction of quantum mechanics. I assume that everybody in this room have learned quantum mechanics at some point, but does not necessarily remember it well. So this slide is supposed to serve as a reminder. In quantum mechanics, we have basis states and general states. And I use a system of n spins or n qubits as an illustration. Each qubit can be in state 0 or in state 1. And if there are 2 qubits, there are 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1. And the state vector is a superposition of those states or linear combination of those states with some complex coefficients. Those coefficients should add up to 1 if we square them. The square of a coefficient is the probability of the corresponding basis state. And this is one example of a superposition. One can also describe states by the density matrix. It's an operator made out of the state vector like this. And this description is more convenient because it can be reduced to a smaller system. For example, if we're only interested in the state of the first qubit, we cannot define the state vector of that qubit alone, but we can define the reduced density matrix of the first qubit. Tensor product is an important mathematical construction that describes putting 2 small systems together. We can multiply states like this. We have 2 state vectors, state vector of the first qubit and of the second qubit, and we can define their product. Not every state of 2 qubits is the product of states of individual qubits. For example, this state is not a product state. However, we can act on states with operators. And those operators can be multiplied regardless of whether we act on product states or not. For example, we can consider the tensor product of the identity operator and the Pauli matrix sigma z, and we get this. And in physics, the usual notation is sigma z2. 2 means that sigma z acts on the second qubit, or the second spin. An important thing in quantum mechanics is measurement. An experiment is usually set up in such a way that we start with some initial state, evolve it for a certain time period, and the evolution is governed by the Schrödinger equation. The overall state change over the given time period is given by the evolution operator U, and this evolution operator is the exponential of the Hamiltonian. If the Hamiltonian is time dependent, one has to use the so-called time-ordered exponential, but that is not important for my talk. After the evolution is done, we can measure some quantity. There are different types of measurements. A measurement usually gives some number, but let's consider the simplest form of measurement, a yes or no measurement. We could measure, for example, whether the first qubit is in state 1 or in state 0. 1 means yes, 0 means no. We can specify the measurement by specifying a projector. This is a projection operator. And given a state, quantum mechanics states that psi has the following probability of the measurement to find the outcome yes. The probability of the yes outcome is given by the matrix element. We apply the projector to psi and then multiply by psi again. Consider the inner product. It can also be expressed in terms of the density matrix. And the evolution starting from the initial state followed by measurement can be expressed like this. We plug this formula in here and we get the final expression as a trace. And this expression contains something called pi of t. It's the projection operator evolved backward in time to the initial state when we can apply it to the state description rho, which is a density matrix. Now, the probability is a special form of a correlation function or a correlator. And the general notation for correlators is this. If we have some operator A and some state described by the state vector psi or the density matrix rho, we can define A in angular brackets by these formulas. Now, we'll use this notation to describe a simple process and its outcome. We start with initial state psi, then we apply operator x, then we let the system evolve for time t, and after the system has been evolved, the final state is a function of the initial state. And then we can perform the measurement, and the measurement is done in the real world, but we can estimate the probability of the yes outcome on paper, theoretically. And it's given by this formula, which can be expressed as a correlation function. It's the correlator of three operators, x at time 0, the projection describing the measurement at time t, and x dagger at time 0. And all subsequent equations will involve correlation functions. This is the way to describe things in quantum mechanics. Let me introduce a variant of the measurement protocol. We may use an auxiliary qubit for control, for a choice of operators to apply. We start with the initial state psi in the main system and some auxiliary state of the auxiliary qubit. It has parameters C0 and C1, and the auxiliary qubit is used to select between two operators, select x0 or x1, depending on whether the auxiliary qubit is 0 or 1. And the selection process is described by a certain operator that involves both the main system, x0 and x1 act on the main system, and the second parts act on the auxiliary qubit. And we get this state, then we let the system evolve, perform the measurement, and we get a correlation function. The important point is that the correlation function in general contains different indices, j and k. So there will be a cross correlator between x0 and x1. That's how cross correlators appear in experimentally observable quantities. They appear when we actually have a slightly bigger system. One can generalize this by introducing a general state that is a product of the system state and a device state. Then we evolve this combined system with the combined Hamiltonian that includes some interaction between the system and the device. And the details here are not important, but in the end, we get some cross correlators that have a very specific structure. This product of operators depends on times, T1, TP, TS prime, T1 prime, and those times occur in a certain order. First, the time increase, we go up, which means we go forward in time, and then the time decrease, we go down. So in a natural measurement scheme, the correlators do not alternate. They involve going forward in time and then backward in time. But there are also out-of-time order correlators that can be defined theoretically, and if we believe in quantum mechanics, such quantities have some meaning. They were first discovered by Larkin and Ovchinnikov in 1969, and back in those times, people did not think about subtle properties of systems of qubits that can be evolved the way we like. People were focusing on real systems or natural systems that occur in nature. And Larkin and Ovchinnikov studied superconductors. And they calculated a certain quantity for a real superconductor, which of course did not contain any out-of-time order correlators. But then they related this quantity to a similar quantity in a normal metal. And the relation is such that out-of-time order correlators appear. This is a mathematical trick. That's how they introduced out-of-time order correlators. But we can also introduce them by thinking about an experiment with a few qubits. We can say metaphorically that we have operators describing where the measurement and where the change, or the flap of butterfly's wings, and we observe whether at time t, introduce the butterfly at time 0, and observe the weather at time t again, which is described by the product of three operators. First, the observation at time t, butterfly at time 0, observation at time t. And a quantum device can select one observation of the two, and we get a cross correlator like this. It's an out-of-time order correlator. So this is quantum chaos. Now, out-of-time order correlators are related to classical chaos, and that was already observed by Larkin and Ovchinnikov. In classical mechanics, we have Hamiltonian evolution, coordinates and momenta. In quantum mechanics, we have the corresponding operators, Qj, and this operator P sub j is the momentum operator in quantum mechanics, and classical mechanics can be considered as a limit of the classical or the quantum mechanics as h bar goes to 0. And the commutator of two momentum operators is related to the classical Poisson bracket, which is in turn related to the derivative of the final state with respect to the initial state. And if we know that this thing grows exponentially in time, we can guess how the commutator depends on time, how the square of the commutator depends on time. And in fact, if we consider the out-of-time order correlator, which is related to the average value of the square commutator, then there will be some constant term plus or minus some correction that grows exponentially in time. And it will grow until the whole quantity approaches 0. When it approaches 0, then quantum effects become strong. We can no longer use the correspondence between classical and quantum mechanics, and we have to solve the full quantum problem. So this is OTOC in a semi-classical system. It turns out that many quantum systems that do not have a natural h bar going to 0 limit exhibit similar behavior. For example, quantum fields in the vicinity of black hole exhibit this behavior of the out-of-time order correlator. The out-of-time order correlator minus a constant grows exponentially in time. The coefficient in front is small. the S in the denominator is the entropy of the black hole, which is huge. So this quantity is very small at first, but then it becomes large. And when the right-hand side is of the order of 1, the formula is no longer applicable. The exponential growth saturates. But a peculiar feature of black holes is that the Lyapunov exponent has a well-defined value. It's related to T, which is the Hawking temperature, which I will explain in a moment. Black holes have out-of-time order correlators behaving similarly to a semi-classical system, but instead of h bar, we have a small parameter 1 over s. Non-integrable large N systems with all-to-all interactions exhibit similar behavior. And the small parameter is 1 over n. Here, the situation with the Lyapunov exponent is more complex. In most examples, the Lyapunov exponent is small, which means that the dynamics is slow. In general, the dynamics cannot be arbitrarily fast. This number 2 pi times the temperature in dimensionless units is the upper limit. It was shown by Schenker, Stanford, and Moldasena in 2015. The dynamics cannot be faster than that. Black holes have chaotic dynamics as fast as possible. But there are some examples of large N systems which approach that limit. In particular, the SYK model has the Lyapunov exponent that is close to the maximal value, and the correction is small when the temperature is small. As the temperature goes to 0, the correction becomes negligible. So this is the main message. The message is that black holes and the SYK model have similar out-of-time order correlators. In particular, the Lyapunov exponent is the same, and maybe there is some deeper analogy between these two systems. Now, let me accelerate a bit. I'll talk about black holes and then the SYK model. And this is slightly more technical. This slide, of course, is not technical. It's just an introduction into black holes. We can estimate the mass and the radius of a body which will look black in the following way. We can try to send light from the surface of that body to the space, and instead of sending light, let's first throw a ball. A ball with mass m is thrown with the velocity v, which is the escape velocity. For Earth, it's about 11 kilometers per second. And one can calculate the escape velocity by comparing the potential and kinetic energy in the initial state and the final state. Initially, the potential energy is given by the gravitational potential, and the kinetic energy is given by the escape velocity. At the final state, they are both 0, and this gives us this value, which we can extrapolate to the relativistic case where classical mechanics or Newtonian mechanics is no longer applicable. Somehow it gives the exact answer. It gives the gravitational radius or Schwarzschild radius A that depends on the mass of the black hole m like this, and G is Newton's constant. In classical gravity, the correct way to derive this formula is to use geometry of space-time. The proper time, it's an element of length on a trajectory, can be expressed like this. And this expression involves the gravitational potential. Now, we have to use the full theory of gravity, Einstein gravity. And its solution for a spherical symmetric body was found by Schwarzschild. It's given by this metric. The metric has some part that depends on time, the time component of the metric, the spatial component of the metrics, and there are actually two components, the radial one and the angular one. D omega is the angular element. The function f is given by this formula in 4 dimensions. In other dimensions, the formula is slightly different. To understand it better, we can consider the Euclidean version of that metric, or we can consider imaginary time. Instead of minus dt squared, use plus d tau squared and write the same formula. And this is a Riemannian metric on some space. It has an apparent singularity at r equal to a, the gravitational radius, but it's only an apparent singularity. We can introduce this coordinate in the vicinity of that singularity and resolve it using an analog of polar coordinates. So the imaginary time tau is kind of like the polar angle. And at the horizon, when r equals a, the circle of time vanishes. It shrinks down to a point, but nothing drastic happens actually. It's just a singularity in the coordinate system rather than in the space-time itself. In Lorentzian time, the picture is similar. One can define lines of constant r. These are green lines and lines of constant time, the blue lines, and one can map the Schwarzschild metric to a metric in this wedge. This wedge doesn't cover the whole space, unlike the picture on the left. It only covers a part of the space, and there are polar coordinates, but and myself. And this simple quantum mechanical system has a collective mode equivalent to Drake-Hooft shock waves, but in 1+1 dimensions. This is a formal description of Majorana fermions. Majorana fermions are generators of a Clifford algebra. These are the defining relations of Majorana apparatus. One can consider representations or the representation of this algebra using the Fock space, and one can express the action of chi j in terms of the action of lowering and raising, or annihilation and creation operators. And this is an illustration. When we apply a creation operator, we put a particle in a box, and we apply another creation operator, and we put a second particle in another box. The full definition of the SYK model is here. It's a quartic Hamiltonian, and it has random constants, random interactions. The average value is 0, but the second moment is not 0. It scales like 1 over n cubed to have a nice thermodynamic limit. And the randomness helps to solve the model. One can consider similar models with some specific interactions. Now, let me mention some interesting properties of the SYK model. The first property is fast dynamics at low temperature. And that is why the dynamics is slow, because it's determined by the interaction strength rather than the temperature. Fast dynamics means that its speed is determined by the temperature. When we go to low temperatures, the system forms a so-called spin glass, and the dynamics is exponentially slow. There are other models like Fermi liquids, which have slow dynamics at low temperatures, but not exponentially slow, only quadratically slow. The SYK model is special because it's a non-Fermi liquid at low temperature, and that was the great insight by Sachdev-Igne in 1992. And I used this model and studied it in a slightly different direction, calculating out-of-time autocorrelators. The model is solvable for large n, and this is the exact interval of parameters where the model is exactly solvable. It has emergent symmetries at low temperatures and large n, and it has an approximate diffeomorphism symmetry, diffeomorphisms of a circle that is broken to the group of Möbius transformations, preserving the circle. And the symmetry breaking is both spontaneous and explicit. There is no explicit symmetry breaking at 0 temperature, but the symmetry is also explicitly broken. And the low energy states are described by this coset. And in this coset, we can define a collective mode that turns out to be equivalent to two-dimensional gravity. Now let me go through a few very technical slides. This is how the SYK model is solved. It's solved by using Feynman diagrams. And Feynman means averaging over the Gaussian distribution of interactions. One can consider various diagrams and select leading diagrams. Some other diagrams also exist, they are suppressed by negative powers of n. If we write down the diagrammatic series only including leading diagrams, it has a special structure. This diagrammatic series can be written like this, and it's already transformed slightly. I use thick lines, which include a bunch of other diagrams with thin lines. Each thick line is the sum of many diagrams. The thick line is the full green function. Then the diagrammatic series is just the geometric series with sigma given by this, results in the Schwinger-Dyson equation, which should be combined with this equation. And these are just functional equations that can be solved on a computer. And one can obtain a solution graphically. One can calculate the green function. But at long time intervals, a solution can be obtained also analytically. And the trick is that one term in the Schwinger-Dyson equation becomes small at low temperature. The time derivative in the Schwinger-Dyson equation may be neglected at 0 temperature. And that gives the formula for the green function at 0 temperature, first obtained by Sajdev and Ye. And one can extend it to small but finite temperatures. But the most remarkable feature is the existence of a soft mode. If we look at the Schwinger-Dyson equation, neglecting the derivative term, then the solution is not unique. There are many solutions. If G is a solution, then we can construct a new G, which will also be a solution. And to do that, we change the time by an arbitrary function of f. Here I'm using the imaginary time formalism. The time goes around a circle, and the length of the circle is the inverse temperature, called beta. So there are multiple solutions. Each such solution is obtained from the 0 temperature green function, beta equals to infinity, by a certain transformation. And in particular, if this phi of tau is taken simply as 2 pi over beta times t proportional to t, we get the finite temperature solution at equilibrium. But there are many non-equilibrium solutions, and there are also fluctuations. At equilibrium, one can consider a fluctuating function phi, which may be sort of, its deformation is described by the function phi of tau. It's a map from the circle Schwarzschild. The Schwarzschild is remarkable because if f is a linear fractional transformation, the Schwarzschild vanishes. One can relate the Schwarzschild action to geometry. One can consider this is the hyperbolic plane in the Poincare disk model. It has radial coordinate r and angular coordinate phi. And we consider a curve that is pretty close to the asymptotic boundary of the hyperbolic plane. And asymptotic boundary is related to the Schwarzschild. And this way, we can reformulate the Schwarzschild action in purely geometric terms. We have a curve in the hyperbolic plane. It's kind of like a balloon filled with air. And there are two terms in the effective action. The balloon cannot be stretched, and its energy will depend on the volume or the area. And now let's consider thermal fluctuations. And the statistics of these fluctuations is exactly the same as the statistics of the SYK model at low temperatures. One can make an analogy. Now the time is real, not imaginary. This coordinate phi may be interpreted as time, but it's not the physical time. The physical time is given by these green lines. Each green line is a line of constant radius going forward in time, and each blue line is a time slice. And in this interpretation, we can talk about the butterfly effect by considering two trajectories with each other. We can use the left trajectory as a reference, and we can perturb the right trajectory and chaos. Of course, the model can also be quantized, and it will be quantum chaos. And that's the origin. Finally, to clarify this connection, I should say that we have talked about boundary effects. The anti-de Sitter space are boundaries of some space-time. And we can consider an actual theory of gravity. To make it non-degenerate, we need to introduce a new field, so-called dilaton. And qualitatively, the Einstein theory for n equals 3 is rigid. It means that the bulk space-time is rigid and turns them into a deformation of boundaries. And this is the connection between gravity and the SYK model. So if we go the full way, we start with the SYK model, solve this to be a gravitational theory, although a very simple one. It's the so-called Jackiw-Tatel-Boehm theory. Let me summarize. Chaos is a theoretical concept. Direct experimental tests of correlators. The Lyapunov exponent is well defined in the quantum case in certain cases, in particular for large N systems and for black. And these are two examples where such parameters exist. The SYK model is similar to black holes. And finally, if you think that let me describe a related model, which was introduced by Maldacena and Chi. It's two coupled copies of the SYK. And correlation correlators in this is similar to out-of-time order correlation in a single model. And the physical properties of this model are remarkable. This model, we just knock the system slightly. The perturbation seems to be gone. And one can think of this process as the system secretly having some bulk to the right and finally emerges. And it can bounce back and appear on the left again. So to new discoveries that may be possible to test experimentally in the future. Thank you for your attention.
Oh, yeah.
So my question is about, is it possible to implement the first test of simulate the construct a quantum circuit and simulate the forward and backward time evolution of certain many-body quantum systems from simulation? Then can we expect how large the system is going to be to make the test work, and which kind of quantum operations could be treated as a butterfly in the simulation? Thanks.
In a small system with a few qubits, the gates that were applied were randomly chosen. One applies a sequence of gates, then some entangling gate, and the reverse sequence of gates.
Thank you for your beautiful talk. In the spectral theory, the quantum chaos describes the eigenvalues and eigenfunctions of high frequencies on the chaotic space. Thank you.
I'm not sure if there is an exact relation, but there is an analogy. For large N systems, 1 over N is analogous to the Planck constant.
Oh, thank you.
Okay. Other questions?
So there are similar solutions from classical consideration. If you slide inside the horizon, and the solution is not smooth, and the mathematicians can prove there are shock waves in time at the end. So it's actually a classical phenomenon.
Do you mean classical shock waves like?
Yeah, in time.
Do you mean shock waves in a gas or in a different system?
Just inside the black hole. Horizon.
Inside the black hole.
Yeah, horizon.
Yeah, you can find a solution that is not smooth. The evolution of a smooth solution, and the singularity does not develop at any finite time. This is.
Yeah.
Okay, thank you for the talk. I have a question on the quantum chaos on the continuous symmetry. I'm working on math problem calculating the so-called OTOC on the toy model of black hole in the sense of physics, because maybe from the perspective of ADS-CFT and the problem to have a global symmetry on black hole. So I'm the SYK model you mentioned. Thank you.
Excuse me, I didn't understand. You asked about whether it's proper to ask some question. What is?
Yeah. I mean, consider the hidden particle. We always calculate the do similar things when we have continuous symmetry imposed on the system. Yeah, the symmetry of the from some group like the U1 group or maybe SUD group.
There are variants of the SYK model with similar to the conserved electric charge.
Okay, we have to wrap up. So thank you very much for a beautiful talk. We have to meet on time still, 11. Sorry about that. heard it. So please try to sit down. For those who are outside, yeah, please sit down. We need to start the lecture. Where's? Huh? You went to the restroom? Okay. Okay. Okay, let's start with the last lesson. Leslie has been in computer science for over 50 years by now, I assume. Graduated from Cambridge. He's my dear colleague in Harvard for many years. I came after less courage on tackling the most difficult problem in computer complexity and learning freely. She has set a really good model for all us to learn. I think artificial intelligence and all these new subjects are influenced by this. Let's have next.
Thank you. Well, thank you very much for the introduction. So I've enjoyed having Professor Yao this ICBS occasion. I have to mention that as a promoter of mathematics, Professor Yao is absolutely unique in his vision of mathematics being so broad, inclusive, and yet of exquisite taste. So it's a unique combination. So what I want to talk about is a topic on which I've worked for a very long time, and various parts have come together recently, and it's become a book whose title is roughly my title. The actual book, if you follow through the footnotes, endnotes, references, there's a technical proposal there. Also, one can read off an interpretation of current AI, which is different from the conventional one, involves as humans. So the topic is really about humans. Okay, so so he asked in a radio broadcast, can every task done by humans be done by a machine? And so I'll just quote. So he said, it's customary in a talk or article on this subject to offer a grain of comfort in the form of a statement that some particularly human characteristic could never be imitated by a machine. It might smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. But my recommendation is that we take Turing totally seriously, because this wasn't just some idle philosophical comment, but this was really based on his main science. So his main science was what became known as the Church-Turing thesis, that what we understand as computation is really universal for all ways in the physical world in which we can do mechanical information processing. It's not very productive to try to disagree with Turing. There are much more productive directions to go in. And in particular, what's left to investigate? Well, what's left to investigate is to define what either machines or humans actually do. And I think largely unsettled science is to characterize what are human capabilities. What is it that we do? What is it that we want our machines to do? And to my mind, it's amazing that we don't understand ourselves too well. So in particular, this is maybe how we self-identify as a species. In fact, we seem to be obsessed with this notion of intelligence. So when we measure our mental abilities, we call the result an intelligence quotient. When we attempt to emulate our mental faculties, we call it artificial intelligence. Some fear that machines more intelligent than humans could be an existential threat. And in searching the cosmos, we're seeking intelligent life. So you would think that we understand what intelligence is, but in fact, even when experts get together, it turns out that they don't. So famously, the American Psychological Association only wanted to figure out what is intelligence. And one of the quotations from their famous report is that when 24 prominent theorists were recently a very good notion. So historically, this is not mysterious. So Spearman, whose work really inspired IQ tests, and correlation. It's not an explicit definition of how you recognize an intelligent person. So we don't have an algorithm for. We think we recognize when someone's intelligent, but how do we do it? There's no definition. So in some sense, what my notion of educability, no one can define. And for example, I don't think the term intelligence has been useful at all. So Turing gave us a license to discuss humans and machines in the same breath. And this is roughly what my proposal is. But the question is, how do we phrase the question? And I just want to acknowledge the cover designer who summarized the meaning of the book by having this and asking, how did humans get from one to the other? So in particular, the question asked in the book is, what is the cognitive capability that enabled humans to go from the Stone Age axe, Stone Age arrow to computers? And okay, so one can call it the civilization enabler. It's some biological change swept through the human population in a period of a few thousand years. And in fact, probably even in the 300,000 years, which is believed to be the age of our species, to ignore phenomena which are more ancient than human. So certainly vision, locomotion, emotions are all pervasive in the animal kingdom. We share it with other species. This is not what separates us from other species. The way we interact with the world is, most of it has got a much more ancient heritage. So the methodology I use is that of computer science. And very simply, the notions are that we want to deal with functions which are well-defined. So this is just mathematical functions. So input-output functions. So if you claim that some organism exhibits some behavior, then you should specify in what way the situation before the behavior is different from the situation after. So it's just mathematical functions. And the second insistence is that every function you suggest should in principle be computationally feasible. It shouldn't be a pie-in-the-sky dream. Okay. So the prediction that we should do psychology through computational models is implicit in Turing, of course, but psychology journals will be computational. So this didn't happen, and part of the result was that the use of computational models needed is slightly more advanced than what was available then. Okay, so what is this civilization enabler? So of course, in some sense, this question has been asked many times. So for example, there are academic studies of any number of ways in which humans and their nearest relatives differ. There's one website where a bit more specialized. We're looking for cognitive capability that is special to humans and the one that enables humans to achieve the civilization we have. So we're not interested in just any difference between humans and other species. So for example, people claim that animal domestication, so there are many things important in human history which may have been crucial, but again, just because you can domesticate animals doesn't explain how humans do the things we do in advanced technology. By itself, it doesn't explain everything, and many other animals do it. Social learning, so we learn from each other. Intelligence, as I said, that's rather badly defined. So symbols, language, so this must get closer. But again, how we can develop a technological civilization. If you teach an ape language, it doesn't change its behavior. Okay, so is this an overambitious goal? Well, just 3 comments. So what did Darwin say about this question? Obviously, he was concerned about this. So basically, his answer was that if you enumerate all the usual candidates for in what way humans are different from other animals, he said that we're different, success as a species. And so after all this previous investigation, what advantage do we have now to investigate this question? Have usually used what in this room we'd use are rather vague words, okay? And if you combine the vague words, then the notions get even vaguer. So but by being more precise, main idea is that we can suggest more complex hypotheses. So maybe the answer to this question of what is this civilization enabler, maybe just more precise language. Of mathematics, you can attempt to isolate notions which are just what I want to do now is to actually tell you what my proposal is for this civilization enabler, and then at the end I'll give 6 different directions in which, if one takes this proposal seriously, then it's got consequences which are of interest to me. So these will be 6 directions in which I've been driven to think, which I wasn't driven to think before. Okay, so what is this proposed civilization enabler? So it's defined, and the name I've called this but this is a kind of a technical definition where this is the given name. So it consists of 3 capabilities in a context. So the first capability is to acquire beliefs, knowledge, whatever, by generalizing from experience. So this will be formalized exactly as standard machine learning is formalized, and support that one can get started. Okay, so the formalization of this, I'll give all this in slightly more detail, but this is just standard machine learning, if you like. But that's not enough. So the second, I think, combination to specific situations. So this is like chaining together 2 beliefs you have. It's a very simple form of reasoning, where you apply things you know in a new combination. And you do this prompted by particular. And then the third part is that humans can also acquire beliefs, knowledge, by having it explicitly described to us by others. So I can acquire a belief by having my own experiences, seeing examples. Science works, so I can go to a course in, say, quantum mechanics, and I learn lots of theories which I certainly can't have deduced from my experiences, because they were deduced from experiments done with great effort by others, instructions, recipes, rather readily. And this is a part which other species have text, because if you can do these 3 things in some very trivial context, like a world in which there's, say, 1 pixel, then that's not very useful. So I'll explain all this. So all this knowledge has to be relevant or to scenes with multiple objects, so we can analyze a position where we can take instructions from someone else and kind of execute them. So one plausible hypothesis would be that we acquired this perhaps in one of our predecessor species, So our own species apparently is about 300,000 years old. I suspect our basic capability for these three things combined in the appropriate way is very ancient. It's probably been with us from the beginning as a species, but it's just taken a long, long time to get rolling like a snowball rolling, because this aspect of exchanging knowledge only gains you a lot if you have lots of knowledge to exchange. Okay, so just to explain in slightly more detail what these three parts of the proposal are. So one is generalization from experience. This is exactly what I call standard machine learning, where you've got a learning algorithm. Deep learning is an example. You're given some training examples with their labels. You're given pictures labeled whether they show an elephant or not. And what this algorithm produces is another algorithm called the classifier. And then the classifier, given a new example, which is not labeled according to the category, whether it's an elephant or not, this classifier will tell you whether it's an example or not. So this is learning by example. But one has to formalize this a bit more. And certainly one important fact, which theoreticians and practitioners know, is that this only makes sense if you specify a world in which the learning happens. So D would be a source of data or a probability distribution. And the magic of machine learning, of course, happens when the examples come from from the same world as where you're going to test them. Okay, so if you learned a lot, but you go to a different planet, it may not be useful. So one needs to formalize this. So the formulation I use is the probably approximately correct model of learning, which basically the main quantitative requirement is that by making more effort in the learning, so computational effort here is both processing the classifier, you want the prediction error to decrease with more effort, but you also want it to decrease fast enough that you're well rewarded. So in particular, the requirement is that this be some algebraic law. So the more effort you make, the better you're rewarded. And in particular, what an algebraic law says is that supposing with 10 times more effort, you halve your error, then if you make 10 times more effort still, then you want to halve the error again. So for certain theoretical learning algorithms which can be analyzed, exhibit this property. So the reason why AI companies spend such enormous amounts of money on training is that they find that however much money they spend, if they spend 10 times as much money, they get rewarded a little bit more. The importance of having a mathematical model of what you're doing is several, but I'll just illustrate one thing which I think is relevant, which I've only recently fully appreciated. So the way I've sketched the definition of back learning is that it's about generalization. If you've seen examples, how do you predict some new examples? So it's about generalization. Now, if you took a less formal view of machine learning, then you think of human machine learning algorithms can't do. So generalization they can do, but people say, why don't they explain what they're doing and make humans can make predictions about situations which don't look like your previous experiences. So how does that happen? Okay, so the fact that current machine learning doesn't do everything people wish is a suggestion that obviously we have to do something else beyond this learning by example. But I think the important thing algorithms just for this task of generalization. So, so present machine learning, this back learning model, and this practical implementation of it, it's all been focused on generalization, not on the others. So, for example, I suppose no one knows, and this is what people are trying to investigate, but maybe they're not good at any of the others. There's no reason to believe that they're good at anything else besides predicting the next token. So predicting the next token seems to imply whether you should listen to the words is a different question. Okay. So, so just one comment which goes a bit back to the practice of AI, that machine learning algorithms are hard to understand, or how they work in particular cases is no mystery. So the practical algorithms currently used, like neural nets, so the main point is that they can represent functions that can be used for cryptographic encoding, which are conjectured to require exponential time to learn. So the practical learning algorithms are heuristic, which work some of the time. So in a setting where many things are not learnable, suggests that it's very hard to figure out exactly which data sets are good and which data sets are bad. So the mystery of why a data set is good for deep learning, the mystery is almost in the data set itself, and the fact that we can't identify. We are in a similar situation, that heuristics are used all the time when we don't understand exactly why they work, but that's fine. So I think for learning, so the fact that given a data source, we can certainly test whether a learning algorithm has succeeded, but just testing it on more examples is the rational reason for relying on them, and worrying more about what a side remark. So let's now go back to the main theme. So the main theme is that we're trying to explain what this notion of educability is, and the first part was standard machine learning. So the second part is a notion of reasoning on what you've learned, and here the main difficulty is that when we learn, our beliefs are uncertain. It's different from standard logic, and so here I use a formulation which I came up with some time ago called robust logic, and the goal of this is to mimic standard logic, in that what you really want to achieve is that in standard logic, but here we'll have to redefine it, and everything we want to be computationally feasible. So basically what this will boil down to is that we will, instead of having one big, let's call that soup box, so here I'm saying that probably doesn't quite work. What we really are is many boxes, and so for example we could have a separate learning box for learning each word of your language. And oops. How do we do this? And just to emphasize what we're trying to do, that is not quite trivial. So there's a quotation attributed to Winston Churchill that true genius resides in certain hazardous in the world, and all the time have to resolve uncertain information which they've learned. So this is some very basic capability, which for a single learning box, we have the standard notions of generalization. So what we want with this robust logic is to have the same, but also have some soundness guarantees when you chain together two beliefs. And very basically what you hope for is that if you've got two beliefs which are supported by your data to 99% accuracy, then when you chain them together, you want some lower bound on how much you should rely on it. And maybe it's 98%. So you want some principles for crow doing some difficult cognitive task, where it's got some bottle and some water, and wants to get a seed from the surface of the water, and it figures out how to pour some more water in the glass. And the point here is that that the information which this crow is faced with, you have to put it in the crow has to understand. So this will consist of separate objects. There's a seed, there's water, there's a glass, there's a water level with some relations, and this all has to be understood by the crow. We'll learn from cases with very partial information. So when this crow sees the situation, it sees the glass, it sees this and that, but most of the other things in this environment are unsaid. So this is the context, and just a quick illustration. So how this mind's eye works is that you, at any moment, these blue circles represent. So you may be thinking of your dog, and you may be thinking of a second object which your dog likes, and you conclude from your knowledge in your brain that it must be a bone which your dog likes. Now, instead of standard logic, in this robust logic, the rule which you invoke to deduce bone will be a learned classifier. Okay, so you will have learned some expression whose output is bone or not bone. Okay, but actually, one important consequence is that in machine learning we learn, but these you can still train together. And the idea is that in your mind's eye, you will you have a situation described like a dog likes, and then you'll use the learned knowledge in your brain to fill up the diagram and make predictions which presumably will be true about the world. Okay, so just one comment. So humans can answer questions like examples of Greek philosophers with their domestic appliance, for example. Okay, so how do we do it? So we do it by presumably training together some facts we know, which we know independently, which we will have learned. So one thing which robust logic does supply is a principled way in which you can do this kind of reasoning. Okay, okay. So and then there are some theorems about this. Okay, but again, let's go back to the civilization enabler, and this. So the third part was being ability of receiving an explicitly described program or instructions, recipes, a formula, and like a universal Turing machine, being able to evaluate them. Okay, and so I'm saying educability is the realization and integration of these three capabilities. And going back to the last thing, so the clear upside has this enormous advantage that discoveries made with painful and costly experience can be shared very efficiently. There's no chance that we could have discovered all of science if we couldn't share knowledge. Also important, I think, is that some of the discoveries are very general, like new methods of reasoning, like arithmetic, needed to be discovered before we could do any kind of quantitative science, and the spreading of such simple new methods of reasoning are very things, but also complex cultures. Okay, so just summarizing this with a diagram. What I'm saying is that biological entities live in a complex environment. Is that it learns from the environment to predict the same environment. Okay, so when a snail learns about its life, where to find food, it's got examples of good behaviors, and assuming the world doesn't change, it's safe. It's adapted to the real world. But this third part of this educability framework, where we receive programs from other people, that's something new and different, but whether it's true. It could be false. They could be lying to you. And in general, it's very hard to test. Okay, it doesn't come with a guarantee that it's tied to the world. I'll say something about this in a second, but the point of basic machine learning and robust logic is that these things are really tied to the world in which, to the world of experience. Okay, so now quickly I want to go and 6 directions which I think follow if you take seriously this kind of proposal. And so the first thing is the only learning and training, which I think are very ancient in evolution on Earth. The behaviors are grounded in experience, they're kind of safe, we've adapted to the world. But if we can absorb instruction from others, then it's very different. So if someone tells us what happened on the other side of the world, we can't rush over to check it out. We just have to believe it or not believe it. Similarly, if someone tells us the outcome of some experiment, but this makes us easy victims of all kinds of false beliefs, ideologies, false beliefs, conspiracy theories. And I don't think that, so in these discussions, often people blame the guys who tell us false things, but here the emphasis is that there's a fault in ourselves. We have to understand. So the fact that we go around with this great capability to analyze the world, it's much harder to test whether something is fact or fiction. So I don't think it's a fault of my model. I don't think it's a fault of evolution. I think there's a basic inherent difficulty that it's very hard to test what's true and what's false. And somehow we live with this imbalance of incredible abilities to absorb information and to run with it. Okay, that's item one. Okay, so item two, popular question. Well, if this educability is real, a sub-question is, well, if this thing is real, then there must be a way of testing it. How do you recognize? Very, very simple. The way in which the proposal is very simple, in that most tests test for, you go into a test, and you test it for some previous knowledge, or you test it for some trait. But here, you'll be tested for how you process the knowledge, you understand it, and draw conclusions. So the goal of this kind of test is kind of different from most tests. So the only trait this would test for is your trait of being educable. Okay, so it's a comment. So in a typical IQ test, you may have some question like, if apple is to seed then? Well, this wouldn't be an educability test because I'm testing your previous understanding of some relations. I'm not telling you anything new, okay? So I'm not testing your form. I give you some information, how well can you interpret it? But this is one which came up first from the web. And again, it appears that these tests are designed to test your vocabulary, for example. But that's not the idea. I really want tests which you give for over a semester is a good educability test. So we have to be broad in how we think about this. Okay, so number three. So educability has many parameters. So one consequence is that as a mathematical model, there are many. So even in machine learning, standard machine learning, there are parameters where you investigate, where you inspect different situations and update them from your learned knowledge. Parameter is belief choice, by which I mean that if you're a standalone system, and even if you just learn from examples, or you believe people's theories, how do you decide whom to trust? Okay, so this is systems, having a carefully composed training data is essential. So of course this is something which psychologists have investigated a lot about humans. So we have sophisticated ways of deciding who to believe. There are parameters also for how you combine these concepts and somehow make the learning easier for the learning algorithm. So this is some notion of imagination that, in science, many concepts can form new concepts by combining as conjunctions old ones. That's a parameter. And certainly a trained system will have some reasoning methods in. So for example, expecting it to discover arithmetic or probability theory is probably too much. We can just program that in, just like we humans have been taught these things. So these are parameters, and the main thing to say is that having many parameters is not a bug of this model, I don't think, but it's a feature of cognition. We're all competing in. We've all got different education. As academics, we're specialists in different areas. In this sense, these are like different parameters. It's the nature of the possibilities of being educable. Okay, computers at some date will become so smart that they'll treat us as animals. So the arguments for this usually start something like this argument of I.J. Good, that let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any man, however clever, ... Way of saying it is that in these arguments, there's always the notion of this idea of ultra-intelligent something which we can't define, something which we don't understand, something mysterious, something to be feared. But if we define intellectual capabilities in terms of like prosaic, understandable components like I've tried, there's something much less to fear, okay? So these machines will do things we understand. Maybe they'll do it faster on a bigger scale, but you know, we'll understand it. And so, for example, it could be that the components I've described are the main components. Maybe that's all there is. But a unique, ultra-intelligent machine dimension, okay? Just like we're intelligent, sorry, I shouldn't use the word. Our cognitive capabilities have gone in different directions. We're capable of different things. We're better or worse than each other in different ways. That's going to be the same with machines. And so the machines built will have the same range of parameters. So studying human behavior is difficult. So in social sciences, the social sciences are different from the physical sciences. Like theories come in different flavors, like different political flavors. Sometimes social science goes what we think is badly wrong, currently do, although in fact some very prominent statisticians were the main practitioners. So what do we have to say about this? Well, so the main problem seems to be that it's very hard to draw conclusions about human behavior that are transferable in time and space. You may do very rigorous experiments on humans, but then if you do the same experiment at a different time and location, you get the same conclusion. I think that's the main problem. So the contribution here is that at least I've given a word to explanation. So I think the explanation of why this is so difficult is because we are so extremely subject to nurture. Okay, so the ways in which we can change our behavior, change our beliefs is extreme. And this educability notion, I try to spell nurture as some vague notion. We can actually try to understand, you know, in what ways are we really influenced by our environment. Okay, lastly, and even more briefly, so obviously this is talk about the science of education, but mostly in terms of doing extensive surveys, trying different methods in the real world and seeing what works best. Certainly very important, but one would think that one should also study the underlying processes which we use when we're educated. So thank you.
Yeah.
Thank you so much. I have a very simple question. Do you think so-called robust logic would concern some elements related to behavior emotions? Thank you.
Yes, because I think as long as your emotional responses, you may see something from which you predict something, from which you predict something else, which you don't like, is dangerous, and then you're in a state of fear, for example. So certainly, I mean, I think our emotional responses are very much tied in with our cognitive capabilities, and the simple training, I think, is fundamental. Yeah, so probably all mammals.
Okay, second question here.
What are the changes that we should make in theories and practice of education today?
So I think this is more a call for future research. So I think we should investigate how humans learn, a notion which people recognize to be a reflection, a useful reflection of some real world thing. Okay, that was the big question: is can we improve the educability of a population by doing something different? And we don't know, and obviously we want to change the educability in further. But it's a fantastic question.
Thank you. Thank you.
So do non-human animals lack educability, or do we differ from them in degree?
Well, so by the time you add being able to execute a program you're given and being able to represent everything symbolically, I think the combination loses other species. So certainly you can get animals to follow fairly complicated sequences of actions, if you got a dog with a name, it's some sort of very beginnings of a symbolic naming, if your dog can recognize it. But the way we can, you can give me some instructions, you can tell me some formula in mathematics, and I can interpret your symbolic names and execute your formula. I think that combination is far from other species, to my knowledge.
I was wondering whether the difference between animal and human could not be explained without bringing in the biological component. For example, could it be where we are now in the future?
Well, I think the point is that I think it's hard to imagine our culture without having the biological capabilities which I've described, of being able to share knowledge of this level of complexity, of sharing instructions and formulae, and describe relevant to abstract notions. So I think to get to this our current state of activity, I can't imagine it without having this kind of capability.
Okay. Other questions? Yeah.
Yeah, so I'm not sure about the individual level, but it feels like humanity as a whole works like a big talk, and it looks a lot like what AlphaGo was doing when he was learning how to play Go by playing against himself. So my question is whether, I mean, from this analogy, you think that AI machines, I mean, learning machines are going to develop conspiracy?
One interpretation is that one could try to analyze our overall culture as one totality. So I was looking at each individual's capability which is needed for this. Okay, but I think you're implying that one could look at the overall culture and see that as something evolving. Machines. Well, so my brief answer is listen to Turing. He said that whatever humans can do, machines can do as well. So there's no reason that they're good questions. So I think to those I'd say, we don't want machines to do that, and I don't think machines will naturally do that because they're ill will towards us. So that's the kind of issue which we need to keep under control, I think.
Thank you for your talk. I have a question. Can AI lie to us, or when?
Well, I think for current systems, if the question doesn't make much sense, I mean, it's just running its algorithm. So certainly, I don't think current systems know when they're wrong. Yeah. So again, I mean, okay. So that's the answer about current systems. If you say what's possible in the future, if you try to make something, then again, listen to Turing. You could make a system like that if you wanted to, in any version. Nothing fundamental. So the educability framework gives you some range of parameters for possible AI systems, I think, and they're under some constraints. And I think one of the constraints is that a standalone system will find it hard to find out what's really true in the world if it's just told that. So there are limits to what absolutely. Okay.
Other questions? Yeah.
So following on that question, like ChatGPT would make up the references, literature reference, as if they are true and like which.
Well, yeah, no. I think that's okay. So I try to address that. So one thing I said is that these large language models, all they guarantee is to predict the next word and produce smooth text. You shouldn't listen to what they tell you. You shouldn't listen to the words. If you care more in the reasoning. So I think there is I think for AI, I think the obvious recommendation is to invest more in making AI trustworthy, in that it should be more reliable, keep facts straight, learn many of the relations in there. in there. So they don't actually learn which paper was published in which journal, but somehow from some averaging they make something up. Okay, so they just never went in the system, the truth about that relationship.
Okay, last question. Yeah.
That a framework like educability can help the state of studies in the social and political sciences, the theories that have certain soundness and things like this. I'm not trying to put you in a bad political spot, but since you came up with this framework, can it be used to really venture into this, let's say, social sciences and tell them, you know, you come up with something that you call theory, quote unquote, but it lacks the Aristotelian characteristics of theory, and implications are for policymakers.
Well, you have to understand what the human is, or what his behavior is. So this is one kind of description of what human behavior is. And if it's an accurate description, a useful description, then surely it should influence social sciences. That, you know, when we just, you know, people have said for thousands of years that the important thing is to understand ourselves.
Okay, well, we conclude this part of the conference for the speeches given by our 6 great awardees. I'm grateful to all of them. I should mention that people on the street were saying that we are running a great conference with the greatest mind in here. So I'm happy that it's already propagated to the whole country. And I wish that a great talk. Thanks.